In our lesson today, we're going to be working with percents and applications with percents. And the first thing that we're going to need to be able to do is to identify the part, the whole, and the rate for each problem that we work with. And there's some tricks that we can use to help us identify those. One big thing that you can do is look for the words is and of. The word is attached to the part, and the word of is always attached to the whole. Okay, the rate is your percent, and that's always going to be followed by the percent symbol. And so looking at this first example, it says, what is 15% of 200? Well, 15% right there, that is the rate R. Okay, and now just look for the two words that I talked about, is and of. What is? Well, that's our unknown here. This is the part. And of 200, of is attached to the whole. Okay, and so in order to figure this out, we'd have to set some variable equal to 15% times the whole value of 200. In example B, again, we're just trying to identify the part, the rate, and the whole. 25% of what number is 50? So again, we can see the 25% there. That's going to represent our rate. Of what number? Of is attached to the whole, so the whole is unknown in this example. And is 50, that's our part. Is attached to the part. So 25% times some number is going to have to equal 50, which is the part. In example C, 20 is what percent of 40? So again, what percent? Okay, well that's the unknown this time. The rate is unknown. Okay, but 20 is attached to the part of 40, so of has to be the whole. So again, part is going to be equal to the rate times the whole. 20 equals some percent times 40. And in the last example, 15%, which is our rate, of what number? Of is attached to the whole, is 75, so that's going to be the part. 75 is going to be equal to 15% times some number. And notice that I've set all of these problems up the same way. Part is equal to the rate times the whole value. And that's what we see underneath here with this percent equation. This is the equation that we're going to be using to help us solve some percent problems. Part is equal to the rate, which is your percent, times the whole value. And the important thing to remember when you're using this equation, the percent must be written in decimal form. So to remember, if you have a percentage like 25%, in order to convert that into a decimal, you're just going to move the decimal point back 2 times. So this is going to be equal to 25 hundredths. In example 3, we're told that in a mall parking lot, 60% of the cars are blue. If there are 300 cars, then how many of them are blue? And so we're going to use the percent equation to help us solve that. We're going to set it up as part equals the rate, which again is our percent, times the whole value. Okay, and we can see the rate was given right here as 60%. Remember, we have to write this in decimal form, so we're going to record that as 6/10. And then we were told that there were 300 cars, which is going to be all of the cars in the parking lot. So that's going to represent the whole value. And P, the part that are blue, is what we're looking for. So all we have to do is 6/10 times 3, which is going to give us an answer of 180 blue cars. In example 4, we're told that Nick has 20 baseball cards. 40% of the cards are players on the Washington Nationals team. So how many of his cards are Nationals players? And again, we'll set up the percent equation. Part equals rate times whole. And once again, the rate is given as 40% in decimal form. That's 4/10. And then we're told that Nick has 20 baseball cards. That's all of his cards, so that has to be the whole value. And P, the part which is the national players, is what we're looking for. So again, all we have to do is 4/10 times 20, which is going to give us 8 Nationals players. 8 of his cards are players on the Nationals team. In example 6, we're told that Jack and Diane had a $40 lunch bill, and if they wanted to leave a 15% tip, then how much money would the tip be? And so this is an application of percentages that we're going to look at a little bit later as well with money and tips. We're going to use the percent equation in this example. We'll use a different one a little bit later on. But again, it's part equals the rate times the whole value. And we know that they want to leave a 15% tip, so we're going to write in 15 hundredths for the rate. And we're told that the lunch bill was $40. That was the whole value of the bill, so we're going to put that in for the whole. And P, the part that they want to leave for a tip, is what we are going to calculate. So if we do 15/100ths times 40, we end up with an answer of 6. Okay, and so we know that the tip is $6. In example 10, Jack and Diane are back. This time they went to dinner. Their bill was $60 and they left a $12 tip. So I want to know what percent of the bill was the tip. So we're going to fill in part equals the rate times the whole in this example. And what percent of the bill was the tip? We're looking for the percent in this case. So I'm going to write R for the rate. And I know that the whole bill was $60, so that's going to be the whole value, and the part that they left as a tip was $12. And so in this case, we've got to get R by itself, so we'll have to divide each side by 60. 12 divided by 60 is equal to 2/10. So R is 2/10, but that's supposed to be our rate. Our rate is going to have to be a percent, so we're going to convert this into a percent, move this once, twice to the right, and this is going to be 20%. And so we can say that the tip is 20% of the bill. One important application of percentages is when you're trying to find a percent of change, either a percent of increase or a percent of decrease. And the equation that we're going to use in order to help us find percent changes is change, which is the amount of change, equals the rate times the original amount. And again, remember that your rate has to be in decimal form. So we're told in this example that Patty got a score of 80 on her first math test. On her second math test, she received a score of 96. What is the percent increase from test 1 to test 2? And so I'm going to use the percent change formula. Change is equal to the rate times the original amount. And in this example, we know that she got an 80 on the first test, a 96 on the second test, so the amount of change is going to have to be 16 points. 96 minus 80 is 16. And we're looking for the percent increase, so I'm going to write an R for my rate. And the original score, Patty's original score, well, the original was the one that happened first. She got an 80 on the first test. And so in this example, we're doing 16 equals R times 80. So in order to get R by itself, we're going to have to divide each side by 80. And when we do that, the rate is going to equal 2/10. And then as a percentage, it's going to be 20%. So we know that the percent increase from test 1 to test 2 was 20%. In example 3, we're told that Tim got a score of 96 on the first test and he didn't bother to study, so he received an 80 on the second test. I want to know this time what's the percent decrease. So again, I'm going to use the percent change equation. Change is equal to the rate times the original. And when we fill in this example, again, well, 96 minus 80 for the amount of change, that's 16 points. The percent decrease, R, is what we're looking for. And Tim's original score on his first test was a 96. So 16 equals R times 96. We'll have to divide each side by 96 in this case. And when we do that, we get a value of R as 16/100ths with the 6 repeated. If we convert this into a percentage, that's 16 6/10% repeated, which is the same as saying 16 2/3%. Okay, so then we know in this example, the percent decrease was 16 2/3%. Okay, now you may have noticed that the test scores for both number 2 and number 3 were the exact same scores. Each person had an 80 and a 96. Their amount of change was the same. They each changed by 16 points. But notice that their percents were different. All right, Patty had a 20% increase. Tim had a 16 2/3% decrease. Why would the percentages be different if the test scores were the same and the amounts of change were the same? Well, the reason why is that these percentages were based off of different original scores. If you remember back in example 2, Patty's test score, original score, was an 80. In example 3, Tim's original score was a 96. when the percentages are based off of different numbers, you'll get different answers. That's why Patty had a 20% increase and Tim had a 16 2/3% decrease. Another application of percentages is when you're trying to find a percent error. And to help us out with that, we're going to use the equation error. The amount of error is equal to the rate times the actual amount. Okay, and so in our first example here, it says, suppose that you guessed that there were 300 gumballs in a jar, but there were actually 400. Calculate the percent error in your guess. So we're going to set this up again as error equals the rate times the actual amount. And we're trying to figure out what's the percent error in your guess. So for the percentage, I'm going to put R for the rate. Okay, we have to calculate how much error there was. How much were we off when we made our guess for our gumballs? We guessed 300, but there's actually 400, so we were off by 100. So the amount of error is 100. And then the actual amount of gumballs in the jar, there were actually 400 of them. And so we want to set up our equation as 100 equals R times 400. So we're going to go ahead and divide each side by 400 in order to get the value of R. And that's going to give us a value of 25 hundredths, which is 25%. And so we can say that there was 25% error, 25% error in our guess. And again, that's kind of high. We always want our error to be as close to 0 as possible. So 25% error, we're going to say, well, we didn't do a good job of guessing how many gumballs were in the jar. In the next example, we're told that Lois measured the course for a cross-country race. The course is supposed to be 15,000 meters. Lois accidentally measured it to be 15,075 meters. So we want to know what's the percent error in her measurement. So again, we're going to use the equation error equals the percent times the actual amount. And we're looking for the percent of error. So R is going to be our rate. And the course is 15,000 meters long. That's the actual length of the course. But Lois accidentally measured it to be 15,075 meters. So if we subtract these two numbers, that means the amount of error, there was 75 meters in error in her measurement. And so we're going to do 75 equals R times 15,000. So in order to get the value of R, we're going to have to divide each side by 15,000. And when we do that, R is going to have a value of 5 thousandths. And then when we convert that into a percentage, move the decimal point over twice to the right, we get half of a percent. And so we can say that there was a half of a percent error in Lois's measurement. Okay, and that's a little bit better in error than the first example that we had. Again, you want your error to be as close to 0 as possible. In the next problem, Jessie estimates the weight of her cat to be 10 pounds, but the actual weight of the cat is 13 75 hundredths pounds. Find the percent error in Jessie's estimate. So once again, we'll set up our equation. Error is equal to the rate times the actual amount. And again, find the percent error. R is going to be our rate. The actual weight of the cat, they told us, was 13 75 hundredths pounds. And we have to calculate how much error there was. Well, Jessie thought it was 10 pounds, but it's actually 13 75 hundredths pounds. So if you subtract 13 75 hundredths by 10, that leaves you with 3 75 hundredths for the amount of error. And so for our equation this time, 3 75 hundredths equals R times 13 75 hundredths. So in order to get R all by itself, we're going to divide each side by 13 75 hundredths. And that leaves you with R on the right. 3 75 hundredths divided by 13 75 hundredths is the decimal 27 hundredths repeated. And now when we convert this into a percentage, again, move the decimal point over once, twice, that's 27. And remember, this repeats, so it's 27 hundredths repeated percent. And so we can say there is a 27 27 hundredths repeated percent error in Jessie's estimate.